Okay, so I think the number of participants stabilized, so let's start. So good morning, everyone. Let me start by thanking the speakers for accepting the invitation to be here. So when I was asked to organize this session on this broad topic of PDEs, I thought it would be interesting in such an event to give a good picture of what is being done and very well done about PDEs in Portugal. So presenting, looking not only at the present, but also at the future generations. So let's start with my colleague at Instituto Superior Técnico, Simão Correia. He's an expert in dispersive equation, elliptic equation, and today is going to speak about one of, I guess, his favorite topics, the nonlinear Schrodinger equation, in this case in spaces of infinite mass. Simão.
Okay, thank you, and thank you very much for the invitation. Yeah, it's been a topic I worked a lot on during my PhD, and so I'm going to present this small work, which still derives from some things I did during the PhD 4 years ago. Okay, so just to start, it's wait. Okay, just let me. Okay, so just to start, let's consider the linear Schrodinger equation, the easiest case. So the spatial domain is the whole space. And given an initial condition, it's an easy exercise from any PDE course to solve this using the Fourier transform. Okay, so you do Fourier transform in the spatial variables, you get an ODE in time, you integrate, and you get this formula for the solution. Okay, and because the evolution is just a multiplication by a complex factor of modulus 1, then you can actually derive this property. So what does this mean? You do any number of derivatives in the physical space that translates to a multiplication by a certain power of psi on Fourier space by Plancherel. And then because the factor has modulus 1, this is exactly the same thing for the initial data. So the norm of any derivative is preserved in L2, which means that the linear flow is well defined in HS for any S. Okay. This property, unfortunately, does not hold in LP. Okay, I've used here quite essentially Plancherel's theorem. Okay, and you cannot use. You can actually show that it's not well defined in LP. There exists initial data in LP for which the solution is not in LP. Okay, so if I cannot define the flow in LP, well, I can ask, what is the largest subspace on which I can define the linear flow? Okay. So what are the known results regarding this? So there's the simple result, which is I just take the HS space, which is embedded in LP. Okay. If you have this condition on concerning P, the dimension, and the number of derivatives, you just use Sobolev injection and you get the flow defined on this subspace. Okay, so but this is the easy answer, it's not the interesting one. Then there's this work of Gallot in 2004, where he considers functions which are just in L infinity, but whose gradient is in some Sobolev space hk minus 1. Okay, and this k is chosen in such a way that the space hk embeds in L infinity. Okay, so this condition k greater than d over 2, you should recognize as the condition for a space hk to embed in L infinity. Okay, but here you can have solutions which do not decay to 0, which can oscillate indefinitely when x goes to infinity. So it's already a much larger space. Okay, and his proof goes through the explicit formula for the linear group. It does a number of computations just to show that the linear group is well defined on this space. But actually there's a general argument which we can use to show the following results. So in the same conditions that ensure the Sobolev injection, and for smaller regularities, just because I don't want to, there are some technicalities regarding higher regularities, then you can define the linear flow on this space. So you only need the largest derivative to be in L2. Okay, the function is in LP, and the largest derivative of order S is in L2. Okay, and the proof is quite general. It's just it's a really simple argument, basically functional analysis, and you can apply it to a number of any other dispersive equation, any equation where basically you have the flow defined in some LP space but not in another. You can use the technique to extend the result. Okay, so having the linear flow well defined on this space, what can we do now? Well, you can consider the nonlinear Schrodinger equation, which is basically the same with a pure power nonlinearity. Okay, there's a plus or minus sign which will be of relevance later. And now the problem is, okay, given an initial condition in some Banach space, can you build a local solution with that initial data? Okay, unique, and usually you also ask for continuous dependence depending on your definition of well-posedness. Okay, so what are the known results for the classical results for this equation? Well, basically, if you consider the space HS, then there's a precise threshold, this 4 over d minus 2s, which is also connected to some Sobolev injection, which must hold. Then if the power is small, then yes, you can build a local solution. Everything is well defined. If the power is too large, then no, you cannot define there may be no solution. The continuous dependence does not hold. You cannot bound the norms. It's a mess. Okay, so this is the classical theory. And now I can ask, well, what happens in this larger space, okay, this subspace of LP? Can we still prove that the nonlinear flow still exists for certain powers of sigma? Okay, and the result is that, well, assuming the same things that give you the linear flow, okay, in the same condition as the HS theory, so the sigma smaller than 4 over d minus 2s, then you can build a solution. So the result extends perfectly. Of course, the proof is a bit more involved because you don't have the L2, and a number of estimates for the Schrodinger equation depend on the fact that you are in L2, so you have to somehow get around that. And there's this extra property which tells you that if the power of the nonlinearity is large enough compared to the P, then the difference between the nonlinear evolution and the linear evolution, which is represented by this operator here, then that difference will be in L2. Okay, so if you compare the linear evolution and the nonlinear one, it will be something in L2, even if none of them is in L2. They're both in LP only. Okay, and this is, you can understand this by looking at the nonlinearity. If the power is very large, then the nonlinearity will have a very small effect on large tails, okay, which is the thing that prevents you from being in L2, is the fact that you have a very large tail at infinity, okay, but the nonlinearity basically does not see what happens in those large tails, and that's why you can actually show that the nonlinearity basically gives you an L2 effect, not an LP effect. Okay, so this gives you the solution locally, and now usually the problem is to understand if you can define the solution for all times. And it's a classical argument. You just need to prove that the norms are bounded, okay, for any positive time. And to do that, you usually need some more information, usually given by some evolution law, some quantity which is preserved by the flow, or for which you know exactly the evolution. And for the Schrodinger equation, there are two classical ones. You have the mass, which is the L2 norm, and you have the energy, which is these two terms. With the sign here, it appears once again, and now it will be of relevance. Okay, and the first observation is that in our context, we do not have the mass well defined because it's the L2 norm and we are not in L2. And the second observation is that in fact, the largest space where you can define the energy is not H1, which is usually the space where people work, is in fact this space. You just need this LP norm and this L sigma plus 2 norm and the H1 dot. Okay. So what are the results which are known? Well, when the sign is negative in the energy, then these two terms may cancel each other. And so you have to somehow bound what happens in the nonlinear term. You use a Gallardo-Nirenberg inequality, which gives you a bound of this term using the gradient and the mass. And you show that that gives you control, at least for small powers. Okay, very well. So that's the classical results. And what you can actually show is that if you are in the space where only the energy is defined, then you can have global opposedness if the power satisfies this condition, which is a stronger condition than sigma smaller than 4 over d. Okay, and the proof, well, you have to use, because you cannot use the mass, you have to use a corrected mass where you have to forget the tails, and hopefully that's will give you something which is still, it evolves in a nice fashion throughout the flow to control that nonlinear term using the same sort of Gallardo-Nirenberg inequality. Okay, so even if the energy, only the energy is defined, you can still show that the flow exists for all times. Well, if the sign is positive, so the two terms in the energy will not cancel each other, the energy is coercive, then just directly the mass plus the energy gives you a control in H1. Okay, it's direct arguments. Actually, you can go a little bit further. You just need the energy, okay? Because the energy gives you control on this space, the L sigma plus 2 intersected with H1 dots. And then once you have this information, that the function is bounded in this space, you can use a sort of persistence argument, which gives you a control in the stronger subspace, which is H1. Okay, so actually you do not need the mass to prove this result. You just need the energy. Okay, but you can even go further than this. So if these results only work for this sort of space, L sigma plus 2 intersected with H1 dot. But as I've mentioned, you can show that the nonlinear flow is well posed in LP with H1 dot. And the P can be larger than sigma plus 2. And if it's larger than sigma plus 2, you do not have the energy. There's no energy and there's no mass. There are no conserved quantities that you can use to control your dynamical system. Okay. And what can you say in that situation? It seems a bit hopeless, but actually you can, at least we've done it for a very specific case, which is the following. So for the cubic nonlinearity, sigma equal to in dimension 3, okay, if the P from the LP space is between 4 and 9 over 2, okay, and notice that sigma is 2, so sigma plus 2 is exactly 4. So we are above sigma plus 2, so we do not have the energy well defined. Okay, but still we can show that the nonlinear evolution is globally well posed in this space. Okay, and the argument, it goes back to the Fourier restriction method of Bourgain in the 93s, and it has been extended by Terence Tao and the I team in the 2000s. And basically you have to, there's a regular part of the solution for which the energy is well defined, and the other parts of the solution, which is not regular, you evolve it linearly, and then you just have to understand what happens with the error term. And if the P is not that large, you can quantify it, it's between 4 and 9 over 2, then you can show that everything works out and you can still control your solution. Okay, so just here are the references, and I thank you very much for your attention.
Thank you very much, Simon. So now we have a few minutes for questions. So if you have some questions, just write in the Q&A or on the chat. If not, I have a question, but I will wait for the participants' questions. So I will give. Okay, my question is, of course, so after this, how about the stability?
Stability of
yeah, in LP, yeah.
For example, for solitons, you mean?
Yes.
Yes, that's actually a very complicated problem. Okay, because usually for the stability, you use a number of variational properties of the soliton,
yes.
which involve the mass and the energy.
Mm-hmm.
And here, well, it's a mess because you do not have the mass. Well, you could try to adapt the arguments for the global opposedness to try to control what happens around the soliton. But that's an open problem. We still haven't considered that.
Thank you. So we have a question, actually two. So if you, so I will read them. So Jose Francisco asks, are there similar results for fractional Schrodinger?
We haven't considered the fractional Schrodinger equation. Okay, and you can do the same sort of arguments. As I've mentioned, the arguments which proves you the existence of the linear flow are quite general, and so you can extend them easily to the fractional case. To show that the nonlinear flow is well posed, well, you would have to go through the proof, and I would say you can adapt it. Okay, but written there are no results regarding the fractional Schrodinger equation.
Okay, and then Jorge Drummond Silva asks, what about the focusing case? Can you say anything about it?
Well, the focusing case is exactly the previous one. Okay, so it's exactly this one. Okay, when the sign is negative, well, we can only show that the problem is globally well posed for this in this range of sigma. And then there are a number of arguments which basically, because when you're above 4 over d, then the equation becomes supercritical in L2. And then because the scaling, you can also consider the scaling connected to this space. And just the scaling argument shows you that it will not be easy. For example, you cannot prove global existence for small data in this sort of spaces. Okay, you cannot to prove scattering. It's also very difficult because the group, the linear group, is not bounded for all times. It can grow in time, so you cannot bound the solution up to infinity. The linear flow, okay, the nonlinear flow is even harder. So the focusing case is truly difficult to handle. And in this one, in the defocusing case where you have the plus sign, it's actually interesting to observe that the L sigma plus 2 norm remains bounded because the energy is constant, even though the linear flow may have this norm growing in time. Okay, so the nonlinear flow actually gives you a better bound for the L sigma plus 2 norm than the linear flow. So it's an interesting observation. But more than that, we cannot say anything.
I will make another question, a very quick one. I will ask a quick answer. You only presented like positive cases. So if the sigma is in this range, then we can do it. Do you have negative one? I mean, do you think this is not sharp? Probably. So it's a limitation of the techniques, or like in this result, right?
In this result, okay. In this result, I'm going to say it's I believe this result can be extended further.
Okay. For more sigmas.
Yeah. Concerning global existence, I think you can extend the results. Concerning local existence, okay, this one, I do not believe this result can be extended further because basically it gives you exactly the same conditions as the classical theory. So probably
but you cannot prove it yet if it's sharp.
But still, yeah, the proof of sharpness for this sort of results, you have to prove ill-posedness. And ill-posedness is not something that is easy to prove.
Okay. Thank you. Oh, so thank you very much. It's time to switch speaker. Obrigado,
So,
Simão.
yeah, you're very welcome.
We'll ask you to, okay, now André. Next we have André.
Can you see my slides?
Yes. Okay, so next we have André Guerra, a former PhD student. So he finished his PhD on Tuesday at the University of Oxford under the supervision of Jan Christensen, and he's going to Princeton next, but right now he's physically in Lisbon giving this talk. Okay, and so today, as you can see, is going to tell us about symmetry breaking and ill-posedness for the Jacobian equation. So thank you for accepting the invitation. The floor is yours, André.
So thanks, Hugo, for giving me the opportunity to speak here. I'm very happy to do so. And yeah, I will talk about recent joint work with Lucas Koch, who was also a PhD student at University of Oxford, and Sally Lindberg, who is at University of Aalto in Finland. And so, okay, so here is the kind of basic question that I'm interested in. So let's say I give you a density F, which I will assume to be positive and integrable, okay, in the unit wall. And my question is, when can we transport this density F to a uniform density? And I also want the transport map to be reasonable. And reasonable means here for me that, okay, I want the transport map to be a homeomorphism. So it will preserve the local structure of the space. Okay, so what I mean by transport map is the following. I mean that my homeomorphism U, the Lebesgue measure of the image of a set under U is equal to the integral of the density over that set. Okay, so this is what I mean by a transport map. And so I just want in the first place to know if these maps exist or not. So this I will call the weak Jacobin equation for reasons that will become clear shortly. So I will normalize my data F. Okay, this I can always do without loss of generality. I just, assume that the average integral of F is 1. And I assume that F is not just positive, but it's actually uniformly positive. Okay, so I will call this condition C for the data. And then it's a very, very classical result, which goes back to Van Neumann and Oxtoby-Ulam in the early 40s, that actually these transport maps always exist. So if you give me a density which satisfies these conditions, I can find a homeomorphism from the closed unit wall to the closed unit wall, which transports the density to the Lebesgue measure. And moreover, I can even choose the homeomorphism in such a way that it fixes the boundary of the ball. So it is the identity on the boundary. So in other words, this existence question it has a positive answer, and one always finds these homeomorphisms. Okay, so now, of course, we are analysts. And so then the natural question is, what can we say about regularity of these transport maps? So in particular, what is the optimal regularity of a transport map which transports F to the Lebesgue measure? And how does it relate to the regularity of F? So you should think that this is kind of a transport problem without cost concerns, right? In optimal transport, for instance, you would be preoccupied with selecting a transport map which minimizes a certain cost. Here, we are not concerned with costs. We are just concerned with the smoothness of the transport map itself. Now, the reason I called the previous equation the weak Jacobin equation, of course, is that if you give me a sufficiently regular homeomorphism, and here sufficiently regular means, for instance, in W1n, then my problem is equivalent to a proper PDE, which is that the determinant of du is equal to F, and U is the identity. Right, this is pretty clear. It's because the Jacobian appears in the change of variables formula. It is the quantity that tells you how areas are distorted. And so if you actually have a derivative, you can formulate a PDE, and therefore our problem is equivalent to a proper first order PDE. And the case where the density is sufficiently smooth is very classical as well, and it goes back to Moser. And then Dacoronha-Moser, and they showed that if you give me a CK alpha, so a Holder continuous or better data, so if you give me a CK alpha data, I can find a diffeomorphism of class CK plus 1 alpha, which solves my problem. So, of course, these diffeomorphisms, they have optimal regularity because this is a first order PDE. So if F is in CK alpha, the solution is at best in CK plus 1 alpha. So, the let's say smooth case is very well understood and is very classical. And I just note that, as always with endpoint statements, this is false at the endpoint. So if you give me continuous data, so k equals alpha equals 0, I cannot find C1 solutions of the problem in general. Okay, so of course, since the smooth case is well understood, what I want to ask is what can I say in the non-smooth case? So in particular, what can I say for data which is discontinuous, right? And so to put things in perspective, you should think that we have a family of 4 related equations. So in the first row here, we have determined elliptic problems. First of all, we have our favorite PDE, which is the Poisson equation. And then we have its nonlinear analog, which is the Monge-Ampere equation. So they are both linear and nonlinear elliptic equations. And here phi is a scalar. And then we have their underdetermined versions. So the first is the divergence equation. And then we have the prescribed Jacobin equation, which is the underdetermined analog of the Monge-Ampere equation. So the point in this table, of course, is that you obtain particular solutions to the underdetermined equation by taking the gradient of a solution to the corresponding determined problem, right? So for instance, if I take grad phi and phi solves the Poisson equation, I will get a solution of the divergence equation, and likewise for Monge-Ampere. So now, of course, the question you ask is, okay, these equations are elliptic, they are beautiful, they have all these properties that we know and love. So what are you doing? I mean, you take the gradient of the elliptic equation and then you will get an optimal solution, right? How can you beat the Poisson equation? And the answer is that you can. So this is an incredible fact, which was proved by Bourgain and Brezis in their celebrated paper in the Journal of the AMS. And they showed that actually for some low regularity data, you can find solutions of the divergence equation, which are more regular than the ones that you obtain by taking the gradient of the solution to the Poisson equation. So it's not enough to just look at the elliptic problem and say that this is the end of the story. It's really not true. And actually the same thing happens at a nonlinear level. So you can also show that for the prescribed Jacobin equation, the solutions that you get from Monge-Ampere are not optimal. So in other words, the underdetermined nature of the equation is what is really making things interesting here. So since these equations are so underdetermined, it's very difficult to limit the maximal possible regularity of solutions. And so kind of a naive idea is to look for solutions which are optimal, they are better in some way, and to do so through a variational principle. So, let me be a bit more precise. So here I am interested in solutions which have Sobolev regularity. And the reason I'm interested in that is because I want to have a proper PDE. I want to have, this formulation with the Jacobian, and to do so I need a derivative, right? So I cannot clearly go below Sobolev space. So I want solutions which are Sobolev. And now let me take 2 dimensions for simplicity. This is, it will make our life a bit easier, but it contains kind of all of the difficulties of the general case. So you can think that this is really without loss of generality. So since I'm interested in Sobolev solutions, the natural energy to consider is kind of a 2p Dirichlet energy, right? So p here is some parameter, which is larger than 1. And so I want to minimize essentially the 2p Dirichlet energy of solutions. So just to be more precise, right, I will say that U is an energy minimizer for F if it is a solution of my equation and if it has the least amount of energy among all other solutions, right? So it's kind of the basic definition. And the good thing about this definition is that it's very easy to see that if you have one solution of the equation, say in W1, 2p, then you get an energy minimal solution. And this is, you just apply the direct method and you use the weak continuity of the Jacobian, and it follows immediately. So if you have solutions with energy, with minimal energy exist. So existence is essentially trivial in this setting. So that is a good thing. We do not have to worry about existence of minimizers. So, okay, so now the question is, are these minimizers actually better, right? So let me just kind of recap quickly the setup. So I'm gonna take some data F in LP, and I'm going to look for energy minimal solutions of this PDE. Of course, the simplest case is when the data has some symmetry. So let's say that I have some radially symmetric data, so it only depends on the modulus of points. And then I can consider a symmetric solution which solves the problem. So this is called as radial stretching in the literature. It takes this form. So it stretches things radially according to rho, and then Z over R is just kind of keeps it fixed. So it's just stretching outwards according to rho. And if you take an ansatz of this form, the PDE becomes an ODE for rho, and then you integrate the ODE and you get an explicit formula. So, the explicit solution is this one, and it is a unique symmetric solution. So in this case, we actually have a very simple class of explicit solutions. And so now you can ask many questions, which were, really, people were really studying this in the late 90s and early 2000s. And so for instance, so here are kind of a lot of fundamental questions that we can ask about this problem. First of all, do energy minimizers exist? If F is symmetric, are the energy minimizers symmetric? And moreover, what can I say about regularity of solutions to my equation, and therefore about regularity of energy minimizers? So if you give me F in LP and P is larger than 1, do I get solutions in W1 to P? And a similar statement when P equals 1, but okay, I have to replace L1 with kind of an improved version of it, which is L log L. This is due to the improved integrability of the Jacobin, but I won't get into that here. So essentially, you can just think about the first question, which is about regularity of solutions. And I note that, you know, because we are in 2 dimensions, the determinant is quadratic. And so if F is in LP, du is at best in L2P, right? So clearly W1 2P is the best regularity that you can expect. So you can think that these questions are about whether one can find solutions with optimal regularity to our problem. And so we have all of these questions about symmetry of minimizers, uniqueness of minimizers in general, and regularity of solutions. Okay, and what I want to tell you is that there is a quantity which controls the answer to all of these questions. So this is our theorem. So this quantity, I call it lambda, and it looks a bit funny. So lambda is the supremum over radii of f of r over the averaged integral of f over the roll of radius r. And okay, here I'm always going to assume as at the start that f satisfies this condition C, so it's normalized and it is uniformly positive. And so in particular, the denominator is not posing any problems, right? So lambda is not blowing up because of the determinant for sure, because f is bounded away from 0 uniformly. So here is our theorem. So first of all, let's talk about symmetry breaking and non-uniqueness. So essentially we have 2 regimes. The first regime says that, you know, in the first regime, we have small lambda, and small means less or equal to 1. So if lambda is small, you have a unique symmetric energy minimizer. Now, if lambda is very large, okay, and here very large depends on P. Okay, so P, remember P shows up in this energy, but it's not very important. You know, P is kind of irrelevant for this statement, but this very large depends on P. So if lambda is very large, you can have uncountably many energy minimizers, none of which is symmetric, right? So small lambda uniqueness, large lambda non-uniqueness, and symmetry breaking. And actually a similar thing happens for regularity. So let's talk about regularity. So let's say I take some data in LP for P larger than 1. Then if lambda is finite, so it can be very large, but finite, then you get solutions with optimal regularity. So they are in W1, 2P. Actually, this symmetric solution is in this space. You know, by the previous part, in general, for large lambda, it will not be energy minimal, but since there is a solution, then there is an energy minimal solution as well. And in particular, this radial solution already has optimal regularity. But if lambda is infinite, then generically, the solutions are not in W1 2P, they are just in W1P. Okay, we also need to work above the critical space for technical reasons, but you can think that we'll go from 2P to P. Right, so we've lost a lot of regularity. So again, finite lambda, optimal regularity, infinite lambda, bad regularity. And moreover, for a generic data in this space, actually lambda is infinite. And this is not so difficult to convince yourself of because lambda has really a kind of an L infinity flavor to it, right? Of course, it's this funny quotient, but you know, you can think that to some extent we are taking the supremum of F over all R, and therefore it really has an L infinity flavor. And so it's not surprising that for a general data in these spaces, this quantity is infinite. Actually. Okay, so this is our theorem. And just to conclude, I just want to say a very small comment about the proof, which is to explain where does this quantity lambda come from. So if we write our Dirichlet energy pointwise in polar coordinates, this is just the square of the radial derivative plus the square of the angular derivative, right? Which is this guy. And we can do a similar thing for the Jacobin. So F is the determinant of the U because the use of the PDE, right? And this is just the wedge product of the angular derivative with the radial derivative. So to minimize the energy, you want 2 things. First, you want your derivatives to be perpendicular to each other, essentially. So if you do that, then essentially you can have equality in Cauchy-Schwarz, right? So if you apply Cauchy-Schwarz, you can just say that this is equal to the product of the absolute values. And then you want to have equidistribution of energy. So what I mean by this is that the energy that you put in the radial derivative is approximately the same that you put in the angular derivative. Because if you have that, then again, you have equality in this very kind of trivial case of AMGM, which is that AB is less or equal than a squared plus b squared over 2, right? So if you do that, then this product is approximately the half of this guy. So this is what energy minimization forces your maps to do. And now let's look at the symmetric solutions. So for a symmetric solution phi, you actually have perfect alignment. So this is an equality. It's not an approximate sign. However, there is no reason for equidistribution to hold. And in fact, it doesn't. And the reason is that if you apply the isoparametric inequality, you see that the angular derivative of your map is as small as it can be. So it is not equidistributing energy. It is putting as least as possible in the angular derivatives and then a proportionate amount in the radial derivatives. And so now the point is that lambda controls the ratio between the radial derivative and the angular derivative. So you have this relation here. And therefore, if the angular derivative is very good as it is, and lambda is small, then you are in great situation, and otherwise you are not. So this is essentially where lambda comes from. Of course, to make this into a proof, you need to work a little bit, but okay, this is what I wanted to say. So thanks for your attention.
Thank you very much, Andre. Okay, so we have time for questions. So we'll wait a little bit for your written questions. Let me just do one while we wait for written questions. So you say that you can build uncountably many, basically non-radial solutions, right? Do they keep some symmetry, like axial symmetry, or they do not have, let's say, any symmetry at all?
Yeah, I mean, so I don't actually know what the energy minimizers are explicitly. I just build maps which have less energy than
okay, then the radial one, but you don't know.
I would think they have things like odd symmetry, like they should be like symmetric with respect to the axis, for instance.
Exactly.
Yeah, I would think something, but I don't know. I mean, we don't prove them. We just build maps with these properties which have less energy, and then okay, it follows that there is a minimizer.
Okay, but that way, how do you prove?
Yeah, this is actually a bit trivial. The uncountably many part. Essentially, what happens is that so your problem when f is radial, it has a one-parameter group of symmetries, which is that you rotate the map both from the domain and then the target. So you rotate the variables, then you apply the map, and then you rotate again, or it's like you rotate, you apply, and then you rotate backwards. So this is a one-parameter group of symmetries. And essentially what happens is that a map is symmetric if and only if it's kind of preserved under this group, more or less. And so if you do not have a symmetric minimizer, you always have like a one-dimensional manifold of minimizers.
Okay, thank you. Okay, I understood. Yeah. Okay, apparently there are no more.
Can I just ask a question?
Go ahead.
Okay. Hi, Andre. Thank you very much for your talk. Just a question concerning exactly your remark that the lambda it has an L infinity flavor. So essentially, you're assuming a higher regularity on F is just not in LP because you're assuming that is finite. So actually, the F has already a higher regularity, and so that would tell me that I would expect also a larger regularity directly for you. Okay, so maybe it's already just a question of any function f which has that lambda finite. Maybe it's just a functional property that you can show that you have some gain of regularity already.
Not really. So for instance, let me give you an example. So for instance, this regime here, right? Lambda less or equal to 1. If you take a function which is radially decreasing, any function, it has this property. Okay, it has to be integrable or something.
Okay.
For instance, so it's not. I mean, you see. So it's not just that. It's this. I mean, it's not just. This is not like an L infinity norm. It's a kind of a funny quotient.
Okay.
Essentially, lambda, if you want, measures how fast f is growing or not. If you want, it's something like that. So if you take a decreasing function, it's not growing, and therefore it has small lambda. But actually, the other way around, it can be. So if you take power functions, for instance, they will have arbitrarily large lambda. The faster the power, for instance. So it's not just measuring. So any LP function which is decreasing has lambda less than 1. So it does not really imply high regularity. It's some kind of structural property, if you want.
Okay. Thank you.
So thank you very much, Andre. This was a very interesting talk. And let's now switch to Diogo Caetano.
Hello.
Is here.
Yeah.
Joining us from Oxford? From
No,
Warwick? No, sorry.
Yes,
Warwick,
yes.
Warwick.
My God, this is a trigger.
Okay, so yeah, perfect. So as I was saying, so the next speaker is Diogo Caetano. He's a third-year PhD student at Warwick under the supervision of Charlie Elliott. He's going to talk about well-posedness for the Cahn-Hilliard equation on an evolving surface. Diogo, thanks again for accepting the invitation to speak.
Okay, yeah, thank you. So my name is Diogo. I'm a almost final year student at Warwick, and today I want to tell you some of the first work I did when I started my PhD about the Cahn-Hilliard equation on an evolving surface. So the structure of the talk will be something of this form. So first, I want to. This is not full screen, is it? Okay,
no, but it's
full screen now. Yeah. So I want to. So most of my talk, the talk will not be analysis intense in any way. So what I want to describe to you first is what the Cahn-Hilliard equation is. So what type of solutions we should expect to it. I want to describe to you more or less how we pose it on an evolving surface, and then I will show you some of the results we have obtained. So this is joint work with Charlie, my supervisor. I just want to talk to you a bit about the well-posedness results we have obtained. And then if we have time, I don't think we will, I can describe to you some of the work I've been doing more recently, part of it with the degenerate version of the Cahn-Hilliard equation. And then there's an interesting gradient flow problem associated with the Cahn-Hilliard equation as well, which if we have time, I would like to describe as well. So again, let me start by explaining to you what the title means. So let's start with the Cahn-Hilliard equation. So this is a classical Cahn-Hilliard equation. So let's just take the equation on a open bounded domain in R3. So let's look at the equation and see what we see from it. So there's some boundary conditions in initial data that I'm not going to really be interested about today. So it's a time-dependent PDE, right? Fourth ordering space, and there's some nonlinearity here determined by a potential F. And this equation was introduced by the end of the 50s by Cahn and Hilliard, right? To try to model something that they call phase separation, not they call, so that is called in the physics community, phase separation binary alloys. And the way that you should think of this is something as we have a component with a mixture with two components, we decrease the temperature of the system and we see phase separation, by which we mean we see a structure on the component where you see one of the components only or the other. A bit like what you see when you mix up water and oil. So it's not what I try to model, but if you mix up water and oil, they don't mix together, right? You see the water and you see the oil. And I'll show you some pictures that can describe this a bit better. And what I claim is that we can look at the equation and really understand why this captures phase separation. So now you have to believe me that somehow the equation can be obtained as a way to decrease this energy, which I will call the Cahn-Hilliard energy for the purposes of the talk. So somehow you would expect, if the energy is decreasing, for the solution to be as constant as possible, right? To minimize the gradient term and to be close to the minima of F, right? And now when I tell you what F is, you will see what the phase separation actually means. So every time I talk about the nonlinearity here, you should think about these two pictures. So whenever I say that I'm talking about the smooth nonlinearity, I mean the purple curve in here, right? So this has two global minima at 1 or -1, the local maximum at 0. Right, so this would be the smooth nonlinearity, but actually the one that Cahn and Hilliard introduced on their paper is this red curve in here, which is thermodynamically more relevant. And this is what I will call the logarithmic potential. But the shape is the same, right? We have two global minima close to 1 or -1, a local maximum at 0. So somehow if you go back to the energy, we want the solution to be minimizing F, so sitting say at 1 or -1 almost all the time and remaining constant. And now let me show you some pictures for you to see exactly this phase separation in place. So this is the video on YouTube of the Cahn-Hilliard equation on the plane, right? So this is what you see. You start with some initial condition, you see phase separation, where the phases are the blue region and the red region, and some small interface. But let me abstain from commenting on the interface. So this is one example. So you really do see the phase separation. A nicer video, for example, this one on a sphere. Right, it's the same type of phenomenon. These are not my simulations, but let's pretend that they are for now. Okay, so this is the type of phenomenon we're trying to model. So this is the last part of the title, Cahn-Hilliard equation. So now that's the second thing I want to explain is what I mean by PDEs on an evolving surface. And again, here I don't want to be too rigorous on how we are formulating the problems in here. So I will also show you some videos about what I mean, and then I will comment, right? So whenever I tell you I'm thinking of an evolving surface, I'm thinking of something of this format. We have some initial surface gamma 0, and we allow it to change over time in a smooth way. right? So we allow something of this form, like you're a dumbbell, you're doing some type of behavior. I don't want to allow something of this form where singularity is developing. It becomes very difficult, right? From the point of view of analysis, people in geometry can think about this problem, but for us, we will think always about a smooth evolution. So we are not allowing for these types of singularities. And this can be, you know, from 0 to infinity or 0 in some finite interval, time interval t. So now putting these two things together, what we're trying to model is something of this form. And now this is not the convoluted equation. It's just an illustration of what we're trying to say, right? So this is an initial surface, and we are allowing phase separation to happen on the surface, right? And at the same time, the surface is changing itself. Okay, so there's two types of phenomena happening at the same time. Okay, so I hope this gives you more or less a picture of what we're trying to model with the equations that I'm going to describe afterwards. Okay, so this is the idea. So what do I mean by this? This should be explained. And then how do we go about doing these types of problems mathematically? And I would say I can think of two different ways of doing it, right? One that's the one I will be following in this talk, which is we have the surfaces given a priori. So there's a prescribed evolution. We have gamma 0. We know how it evolves on an interval of time. So all about it is known. And then we consider PDE on the equation, on the surfaces. A bit more interesting would be to determine the evolution and the equation at the same time. And I will not mention this in the talk. So here we would think about the evolution and the equations for the evolution and the equation for the, you know, the convoluted equation to be coupled somehow, right? So one influencing the other. So this maybe if we have some minutes in the end, I will describe it. If you're interested, please do ask me, because I have an extra slide where I show the equation that we would get in this case. Okay, so this explains the title. So by now, I hope you understand what I mean by the convoluted equation and what I mean by the evolving surface. So let's go to the mathematics, right? So this is the equation I want to consider in here. So right now we have gamma t in here. And this is the same equation I showed you before, right? There's a time derivative in here, fourth order in space, and this is the nonlinearities I showed you, right? Now I'm purposefully using a different notation for the derivative because we should think about it in the way that if we are to account for time evolution in this system, somehow we should account for the evolution of the function, but also the evolution of the surfaces itself, themselves, right? So there's, it's a different definition of time derivative, but it's, you know, it's what we would expect, right? And then we have an extra term in here, which is accounting for local compression or stretching of the surfaces. And this needs to be in here because we want to capture the main essence of the convoluted equation, I would say, which is the convoluted dynamics of preservation of the integral, right? So we can make a calculation to differentiate the integral of the solution at time t, and this is 0, right? So whatever initial integral we start with, this will be preserved over time, right? So this is an essential feature of the equation. I would really ask you to keep this in mind because this will play an important role afterwards, right? And now let me tell you a bit about the results we have obtained. So now I will consider F to be the smooth potential. Remember the purple curve, you know, defined in all of R with minimum at -1 and 1. And then we go on to the logarithmic potential, right? And for the smooth potential, what we have, oh, I forgot to explain something, right? So the equation is fourth order. So we don't really like to work with fourth order equations. So we're going to make a change of variables in here. This is easy to make, right? There's no boundary conditions in this case. So I'm just going to make a trick and call this thing inside here W, right? And then this will lead me to the system of two second order equations, right? So it's much nicer to look at. So W was just, you know, whatever was inside the first Laplacian, right? And what we proved for this, in the case where F is a smooth potential, we have some existence of some weak solution in the appropriate spaces. And we prove uniqueness and the stability estimate for the problem, right? So just some comments here. I didn't tell you what a weak solution is, but, you know, for those of you who work in PDEs, you know exactly what it could mean by looking at the problem, right? It's just the classical, everything would make sense in the classical Hilbert setting. L2H1, it's not exactly the classical Bochner space. It's an adaptation of these spaces to time-dependent domains, right? But this means what you expect, L2 in time H1 in space, right? And the derivative lies in an appropriate dual space to give meaning to the equation, right? So you understand what type of, that this really is a well-processed result, exactly in the same way as we would do it in the classical setting. And for the smooth potential, we have some extra regularity results. In particular, U is actually H2 in space. And if you're paying, you know, attention, this is not surprising to you, right? Because you would say, okay, given W, the second equation determines an elliptic problem for U, F is smooth, right? So we should get better regularity. And you would even say, look, if W is H1 in space, we can do a lot better than H2. And I say, yes, this is true. With appropriate conditions on the surfaces on the initial data, we can go at least, you know, all the way to H4 and obtain a strong solution, by which I mean this holds in L2. Right, and I just wanted to have this result in here because to contrast it with what we will have for the logarithmic potential, okay, where we will not have this sort of regularity. So this is the same result that we have in a classical setting. So maybe now you could argue, okay, this is not very interesting, right? Because actually the evolution of the surface is not playing any role in proving any well-positives for the smooth potential. And now I claim, okay, just hold on a second, because the logarithmic potential will show you that actually the evolution of the surfaces does play a role in the well-posedness. So now let's move on to logarithmic potential. Again, just to go back to the picture, this was the red curve that you saw. It was defined between -1 and 1. It was defined at -1 and 1 as well. But now if you remember, so this is the expression, right? There's some logarithmic terms. I don't want to get into the physics of the potential. But now if you remember that what shows up in the equation is not f, but f prime. And there's an important feature in here, which is that f prime is singular at -1 or 1 and 1, right? It's not defined. So if you want to give meaning to this sort of equation, we would expect, okay, there's a natural restriction to give meaning to the solution of a logarithmic potential, which is that u should be bounded by 1 in magnitude, right? For this nonlinear term to make sense. And maybe some of you now are seeing that this is an issue, right? Because I claim that combining the boundedness of the solutions with the preservation of the integral and the fact that surfaces evolve leads to some sort of problems as far as well-posedness is concerned, right? And the best way for me to show you this is with an example. So my claim now is these three things combined will not show us that it's not possible to make a well-posedness result as general as we did at least for the smooth potential, right? So let's consider an example. So let's suppose we start with some initial condition constant equal to 1/2. Let's suppose our initial surface is a sphere of radius 2. And let's suppose that at some instant time t, our surface is a sphere of radius 1. Right? So now let's try to see what we would, suppose a solution exists, and let's try to use these facts about the solution to see what we can conclude. So on the one hand, we have preservation of integral. Remember, this is what I told you to keep in your minds about the feature of the equation. So on the one hand, the integral time t is the initial integral, right? And this we can calculate, it's equal to 8 pi. If I made the calculations correctly, this is 8 pi. And then on the other hand, we have boundedness of the solution. So this guy here is equal to 8 pi, but u is also bounded by 1. So this is bounded by the area of gamma t, which is 4 pi. So there's an issue arising here, right? There's some sort of contradiction. So what is happening? So those of you who maybe are familiar with these types of problems, maybe understand that the problem really comes from this Cahn-Heeler dynamics that we are enforcing in here, right? In the sense that we are asking for this quantity of time to be independent of time, actually, right? So this is a constant over time. So somehow you would expect u to counterbalance whatever behavior gamma has, right? In particular, if the areas of gamma decrease a lot, you would expect u to increase sufficiently to keep this constant, right? And the problem is that you cannot increase sufficiently in some cases, right? Because u has to remain bounded by 1. So there's an interplay here between the evolution of the surfaces, the boundedness, and the initial condition that has to be taken into account if we are to make a well-posedness statement. And the way we dealt with it is, okay, I just restrict the set of initial data to satisfying some extra condition in here. This encapsulates the classical setting, right? So we are more general than the classical setting, but this is not sharp. This is almost sharp. I could say almost sharp, but anyway, let me not make comments on this condition. And then if we take initial data in here, I can do the same type of result. There exists a weak solution. The solution is unique. I have the same stability estimate. And then I could also have some sort of regularity result. So U is L2H2. And I will leave this as an open question. If you're interested, you can ask as well, where we don't get more regularity than this without extra work, at least. Right? And then here I have a bit of I never really know how to exactly explain this type of set of admissible initial conditions, because I was giving this similar talk 2 weeks ago, and someone said it because it makes it seem that I'm saying, okay, we have the surfaces given a priori, so I'm restricting the initial conditions. And so here I would say I restrict my set of initial data. But someone was saying that maybe the best way to formulate it was that this is restricting both initial data and the surfaces. And the way they pointed this out was that because I told them that, for example, if your surfaces, the area of the surface increases over time, this is always satisfied, right? So they were saying it's not really about the initial data per se, right? There's some conditions involving the surface. So I don't really know exactly yet how to describe this set of initial data, but okay, for the purposes, I think you understand it. What I mean is that for me, at least at the moment, surfaces are given, so it's not, I cannot change them, right? We assume they are given being, smooth at least, and then I restrict the initial data to this set. Right, and I think this will be the end. I'm not keeping track of the time, so I hope this is fine. So yes, the first part of my talk then, the goal was to describe to you the Cahn-Heeler equation as a model for phase separation. Hopefully the pictures really illustrated this and you could see how the equation actually tells us this information. And then the second part was devoted to explaining to you how we treat the problem involving surfaces given a priori, right? I didn't describe when we don't know what surfaces do to start with. And in smooth case, this is the same result as the classical setting. And then for the singular potentials, and in this talk, I only told you about the logarithmic potential, it becomes a bit more interesting. Right? So it shows that there's some things to describe afterwards. And this is everything. Thank you very much.
Thank you very much, Diogo. Right on time, on schedule, let's say.
Perfect. Yes.
So while we wait for our written questions, let me ask you if, do you have in some particular cases, can you study the long time behavior of this? I imagine it's very difficult, but.
Well, this is something we wanted to look at. So there are some papers who do, for problems involving surface, they say, okay, suppose gamma of t converges to some fixed surface.
Exactly, in some sense.
Infinity. And what do we expect? For the kind of equation, we haven't done it. I know that in the classical setting, there's some study on these global attractors and where the solution should converge to. So I don't know exactly what we would get for the kind of equation, but this is interesting, right? We would look at this. We'd be interested in looking at this.
Okay, thank you. Let's see. Okay, there's a question. Okay, by José Francisco Rodrigues. So if you want, you can open the Q&A, but let me also read it. So your evolving surfaces are smooth. How much do you need? While your solutions of cantilever only variation. Well, what are the topological properties for your surfaces?
Well, so we were not very ambitious in this, that we assumed everything everything good was happening. So for the well-posedness, getting H1 solutions, C2 was enough. C2 surfaces, and we did, closed compact surfaces. So we're thinking of spheres, right? Things that people in applications be interested about. So for us, these were closed surfaces, so compact, no boundary, and C2. And we assume that the evolution is C2 as well, so that you preserve the topology over the evolution, right? We were not ambitious to the point where we allow some topological changes to occur. And I don't really know how we would do this. So yeah, this is what I can say.
Thank you. So I don't think we have more questions.
Can I ask a question?
Yes. Go ahead.
Okay, hi Diogo. Thank you for your talk. And concerning the problem where you have that contradiction between the conservation of density of mass and the evolution of the surface. Mm-hmm. So assuming that you have exactly the appearance of that contradiction, there's some time where what happens at that instant. So you have a solution which starts evolving, mm-hmm. but then the surface makes it that you cannot have the solution anymore. At that time, mm-hmm. does the solution becomes just -1, 1 everywhere? What happens?
Well, this is interesting. The short answer is that I don't know what happens, and this is something I've been thinking about recently, which is okay. I definitely can find a solution until the point where that happens, right? And we were trying to think of a type of evolution where you would reach that point and then come down immediately. So how would we overcome this singularity and keep on with our solutions? And the short answer is that I don't know what happens, but I imagine it would be something of this form, right? So you would become constantly equal to 1, say, and then the equation doesn't make sense anymore. The thing is that in the classical setting, you cannot see this behavior, right? Because the conservation of mass in the classical setting is the same as conservation of the mean value, right? Because you have 1 over measure of omega, but here mean value is not preserved, right? You have 1 over measure of gamma t integral a view of t, right? And then when you differentiate, it is not conserved, right? So you cannot capture this type of behavior on the classical setting. But yeah, I don't know what happens, and I think this is interesting. And when I said that my statement was not sharp, it's because of these particular cases. I can tell you that if it remains at 1, say for an open interval, right, you definitely cannot have a solution, because it would have to be 1. If it overcomes 1, same thing, right? Because the areas are continuous due to our assumptions, so it would there would have to be an open interval where it would be above 1 for sure. But if it touches 1, say at 1 point or at 7 points, I really don't know what happens.
Okay, thank you.
So thank you very much. So it's about time to go to our last speaker, José Miguel Urbano. You know, José Miguel, that there's a main speaker called Joseph Urban.
I saw that. Yes.
Interesting.
It's probably Polish. Can you see my screen now? I think so.
Yeah, yes. Now we can.
Good.
Okay. Are you ready? Yeah.
Yeah, all set.
So now I have to play. We close with a golden key with José Miguel Urbano from Coimbra, and he's going to speak about sharp regularity for singular and degenerate PDEs. Thank you, José Miguel. The floor is yours.
Thank you, Hugo. Thank you very much for the invitation. It was a pleasure to see that the future of PDEs is in very good hands. And so today I'm going to talk about regularity for singular and degenerate parabolic equations. And I'll divide the talk in two parts. So in the first part, I'm going to basically do an historical account of qualitative results concerning this type of PDEs and the developments of the last, say, 60 years. And then on the second part, I will speak about quantitative, sharp results for these equations. And this is something I've been doing with different collaborators for the last 6 or 7 years. Okay, so as we all know, regularity for nonlinear equations started basically with the proof by DiGiorgi and Nash of the famous 19th Hilbert's problem in the late 1950s. So what is this about? So the problem concerns the regularity of minimizers for regular problems in the calculus of variations. And this is connected to PDEs because minimizers of regular problems in the calculus of variations, they satisfy a partial differential equation, which is called the Euler-Lagrange equation. And if you differentiate this equation, you see that the first order derivatives of minimizers satisfy an elliptic equation with coefficients. And the problem was basically this. So people knew that if the minimizer is in C1 alpha, then its first order derivatives satisfy an elliptic equation with coefficients that are C0 alpha, that are Euler continuous. And it was known by using Schrodinger estimates that then you could show that the solution of these equations would be, so if the coefficients are C0 alpha, then the solutions would be C1 alpha. So since the derivatives of the minimizer are solutions of the equation, if you prove that they are C1 alpha, then the minimizers would be C2 alpha, right? So if you start with C1 alpha, you get to C2 alpha using Schrodinger, and then you can bootstrap this idea. And so you can go from C2 alpha to C3 alpha and so on. And you could basically prove that minimizers are C infinity, and then analyticity would follow. This was already known also at the time. But the problem was that the existence theory obtained by direct methods in the calculus of variation placed the minimizer only in H1. So the PDE, if the minimizer is in H1, the PDE has coefficients that are merely measurable and bounded. They have no regularity whatsoever. And in this case, you cannot apply Schrodinger theory. So this was the gap between the existence and the regularity theory. And solving the problem would basically boil down to showing that elliptic equations with bounded coefficients have solutions that are Euler continuous. So if you can prove this, then the derivatives of the minimizer are Euler, so the minimizer is C1 alpha, and from C1 alpha you could go up to C infinity. So this was the problem that DiGiorgi and Nash solved in the late 1950s. So they proved that solutions of elliptic equations with coefficients that are only bounded are Euler continuous, okay? They did it independently, more or less at the same time. They were actually, curiously, they have exactly the same age. They were born 4 months apart. So DiGiorgi was slightly older than Nash. They did it totally independently using very different methods. And I want to concentrate on the method that was used by DiGiorgi, okay? So let me say a few words about the method. So the idea to prove Euler regularity is this. So you want to measure the oscillation of a solution in a sequence, say in the elliptic case of balls. I wrote here cylinders because I'm already thinking about the parabolic case. You want to measure the oscillation of the solution in a sequence of balls that shrink to a point, okay? And you want to show that the oscillation goes to zero as the cylinders shrink to the point. And if you can measure how the oscillation converges to zero, then you can drive a modulus of continuity. For example, if it goes to zero like a power, you are able to show that solutions are Holder continuous. Okay, so this is the idea. So it's an iteration method. And the method is based, so there is a picture for this. I mean, this is in the parabolic case. You don't have balls, you have cylinders because typically you have here this, so this is space and this is time. So you have space-time cylinders, but the idea is that they are nested, they shrink to the point, you measure the oscillation, you show that it goes to zero in a certain way, and you derive a modulus of continuity, okay? So the whole business is based on the so-called Kachopoli estimates. So if you have an equation like Degenerate had, an equation of this type, so elliptic equation with coefficients aij, linear, in this case, the equation is linear. The basic thing you have to show is that solutions satisfy these so-called Kachopoli inequalities. Once you obtain these inequalities, you can forget the PDE. So the problem becomes a problem in analysis, showing that if a function satisfies these inequalities, then it is Holder continuous. It doesn't matter once you get this, if the function is a solution of a certain PDE, if it's a minimizer of a certain functional, or if it's just a function that belongs to what we can call the Degenerate class, which is the class of functions that satisfy an equation like this, an inequality like this. Okay, so it's a purely problem in analysis once you get this. So this is what I call the building blocks of the theory, and I want to concentrate on this because I want to show you the difference in these Kachopoli estimates when you go from these linear equations to non-linear equations and then to the parabolic case. But I thought it would be nice to derive the Kachopoli estimates for the simpler case of a linear elliptic equation as Degenerate did. And that's what I'm going to do now. So we have an equation of this form. So coefficients aij, so the equation is linear. And we have two assumptions on the coefficients. So the uniform ellipticity, so for a positive constant lambda, we have this algebraic condition satisfied by the coefficients. So this means basically that the coefficient matrix A is positive definite with the lowest eigenvalue greater or equal than lambda. And then we assume the boundedness of the coefficients. So for a certain capital lambda, we have that the L infinity norm of the coefficients is less or equal than lambda. So a weak solution of this PDE, and of course, I mean, you just multiply by a test function, you integrate by parts. So a weak solution is a function in H1 that satisfies this equality for every test function in H1 0. And to obtain the Kachopoli estimates, what we do is that we choose, so for a certain number k positive. So, I mean, these Kachopoli estimates are basically estimates on level sets. The idea is that you choose this k, for example, equal to the L2 norm of the function, and then you prove that u minus k plus, the positive part of this is 0 almost everywhere, so u has to be less or equal than k, and you get the local boundedness from these inequalities to start the process. And you take a function, say, eta, which is C infinity with compact support in U. So this is basically displays the role of a cutoff function here. Okay, and then you test the equation with phi equal to U minus K plus eta square. Okay, so you take this is the positive part of the function. So this is U minus K if U is less or equal than K, and it is 0 if U is above K. And this is, of course, an element of H1 because the positive part of a function, of an H1 function remains in H1, and this cutoff makes the function 0 on the boundary, right? Because this has compact support. So this function is a legitimate test function. And if you use it in the definition of weak solution, you get this. So integral over u, aij, of course I'm summing in I and j. I don't write the sum to simplify. And then we have u minus k plus eta square xj dx equals 0. Okay, then we take this derivative and we obtain aij uxi u minus k plus xj eta square dx. And then the other term I put on the right hand side. So aij uxi u minus k plus, and then the derivative of this guy, which is this. Okay, and now I make this crucial observation that since I have u minus k plus here, if u is greater than k, then this is going to be 0, so everything is going to be 0. So having u here or u minus k is the same thing, right? Because, I mean, if u is less than k, then u minus k plus is u minus k. When I take the derivative, this is just the derivative of u as it is here. In the other case, everything is 0 anyway, right? So we can write this as aij u minus k plus xi u minus k plus xj eta squared dx. And the same thing here on the right hand side. I can write this as u minus k plus xi u minus k plus 2 eta xj dx. So you see again that, I mean, either this is 0 and then everything is 0, or this is not 0 because u is less or equal than k, right? And if u is less or equal than k, then the positive part is u minus k. When you take the derivative, k is a constant, it disappears, so you get exactly uxi, which is over there, okay? And then we start estimating, and we estimate the left-hand side from below by using the ellipticity constant. So we have here the sum of aij, something xi, something xj, and this is greater or equal than small lambda, the square of the vector. So this is the this is the ith component of the gradient of u minus k plus, and this is the jth component of u minus k plus. Okay, so you bound this from below by lambda integral the gradient of u minus k plus squared. So this is just the ellipticity working. And then concerning the left-hand side, the right-hand side, you bound it from above, right? So you take the modulus, the minus disappears, then you put the 2, this 2 goes out. Then the aij's, the L infinity norm of these guys is bounded by capital lambda. And then you get inside, you get, so you take the modulus of this is less than d u minus k plus this modulus, the modulus of this guy, the modulus of eta, and the modulus of the gradient of eta, okay? And then here you apply Young's inequality with epsilon. So you separate this in 2 parts because now you want to absorb this term, this term, this and this on the left-hand side, right? So you just use the fact that here you use that AB is less or equal than epsilon A square plus 1 over 4 epsilon B square. So this is something that people working in PDEs are very used to do all the time. So this is our A. So we get integral du minus k plus square eta square dx plus something, and then the integral over u minus k plus square, here you don't need the modulus, d eta square, okay, dx. And then you want to choose your epsilon the right way. So here, basically, I want to get here lambda over 2 to bring it to this side. So I'm going to write here, so 4, this guy, lambda. So when this multiplies, this cancels. So I get lambda over 2, okay? And then here I have 1 over 4, this guy, so forth. So I get basically, this is the thing that I get here, the constant multiplying. Maybe I should just put it there. Okay. So now let's do this. So we multiply this here, we get lambda over 2. This term is exactly like this. We bring it to the left-hand side, and we get here lambda over 2, integral over u, du minus k plus square eta square dx, less or equal. And on the right-hand side, we get 2, this guy squared over lambda, integral of u minus k plus squared d eta squared dx. And then we just multiply everything by 2 over lambda. So we get here square, and we get here 4. Okay. Okay, and hopefully this is exactly what we have here. All right. So du minus k plus square eta square, and then a constant, and then u minus k square, the gradient of eta squared. Okay, so, and we have the explicit form of this constant. So it depends, we know exactly how it depends on the ellipticity and the boundedness constant. Okay, so this is the building block of, these are the building blocks of the theory of Digiorgi, which combined with a Sobolev inequality allows us to derive an estimate that we can iterate to obtain first the local boundedness of solutions, and then, of course, doing other things, the Holder continuity. Okay. Now, although the approach of Digiorgi applied to linear equations, the linearity had no bearing on the proof whatsoever. And so it was based, the proof was based exclusively on deriving these Kachopoli estimates and then using the Sobolev embedding and an iteration argument. So it was more than natural that these ideas were immediately generalized. And this was done by the Russian school of Ladizhenskaya and Uraltseva to nonlinear equations of the following form, where not only you have a principal part which is nonlinear, but which grows nonlinearly with the gradient. So this is important. So this grows like a p-1 power of the gradient. So there's a nonlinear growth with respect to the gradient of the principal part. But the basic thing is that the Kachopoli estimates that you obtain for an equation of this type have exactly the same form as before. The only thing that changes is that instead of having a 2 here, you have a p throughout, right? But you still have homogeneous equations. You still have a nice Sobolev embedding in W1P. So basically, you're just going from the Hilbert case of H1 to the Banach case of W1P, but everything works just fine. And the fact that you don't have uniform ellipticity, the fact that the equation is degenerate if P is greater than 2, because the ellipticity coefficient, sorry, the ellipticity coefficient vanishes at critical points, or singular if P is less than 2, because this coefficient goes to infinity at critical points where the gradient is 0, doesn't affect the proof, because you are still able to derive this type of Kachopoli estimates. So the next step was to think about what happens in the parabolic case. So if you add time to the problem, and so you start with the same linear equation as the Georgi, with the time derivative here, and this was done in fact by Nash already, and then by Moser. They proved that in this case you can still do the same thing. So the theory was easily extended in this case, and you see that the type of estimates that you obtain, so now you have these estimates written over cylinders because now you have space and time, but you see that the estimates, they remain homogeneous in the sense that the new terms that come from estimating the time derivative, which are these three terms here. So this part, you see, this is exactly the estimate in the elliptic case. So because of the natural homogeneity between space and time, you get these terms that involve still the power 2 over there. And if you have this type of homogeneity, then you have the right parabolic Sobolev embedding, and the proof can carry on. So this was also done, I mean, almost immediately after the proof by the Georgi and Nash. And I was saying, in fact, Nash proved the results immediately for elliptic and parabolic equations, more or less at the same time. But surprisingly, when you go to the nonlinear case, things do not work any longer. And the fact here is not so much the nonlinearity, because if you have a principal part that grows linearly with the gradients, despite being nonlinear, you are still fine. But when you have a degenerate parabolic equation like this one, the proof does not work. And the reason being that the estimates that you get are no longer homogeneous, because you have, so from the principal part, you get the power p, as in the elliptic case. But now, I mean, from the time derivative part, you get, of course, power 2, right? Because this is what you get from estimating the time derivative term. And the fact that you have different powers here and here, this non-homogeneity does not somehow disclose the right Sobolev embedding to carry on with the proof, okay? And you cannot do it. So in fact, what you need for things to work, you would need to have the power p here as well, and you don't. So this problem was open for more than 20 years, and only in the mid-1980s it was solved, basically by Emanuele Di Benedetto, who introduced this idea of intrinsic scaling that I want to explain to you briefly now. Let me just mention on a very sad note that Emanuele just passed away last May. And so I want this to be also a tribute to his legacy. I mean, he was one of the persons that influenced me the most, and he was a dear colleague and friend. And so, but I think his ideas will remain with us for a very, very long time. So let's try to understand what we have to do to somehow recover the homogeneity in the equation. So suppose your equation would be like this one. So this is called Trudinger's equation. And you see that comparing it with the P-Laplace equation, the parabolic P-Laplace equation, what happens is that here you don't have the derivative, the time derivative of u, you have the time derivative of this power of u to the p minus 1, right? And if you have this, then the estimates, the Kachopoli estimates that you derive, they are in fact homogeneous. And you have, say, you have power p throughout and everything works just fine. So if you want to compare this with the P-Laplace equation, what are the differences? So what is the main difference? So I wrote the P-Laplace equation in this form, right? So you see that here, if I take this derivative, this time derivative, I get p minus 1. And this is supposed to cancel with this 1 over c to the 2 minus p. So you just, this constant is precisely the constant that cancels the p minus 1, okay? So this would cancel with this power. Then you get u to the p minus 2, and this cancels with this u to the 2 minus p, right? And then you just get the time derivative of u. So this here is just dtu, okay? So I wrote it in this form to compare with this equation. So let's say that this is fine because this is homogeneous. So basically what we have to do to make our P Laplace equation homogeneous is to multiply by, we have to just divide by something of this type. So we have to get rid of this term here. But of course we cannot do that because this depends on the solution. We cannot just get rid of this, okay? So, or we have to do this in a rigorous way. And this is the idea of intrinsic scaling. So the idea is that the analysis that you do cannot be done in cylinders that reflect the natural homogeneity of the equation. So in the classical parabolic case, this is r in space, r squared in time. So for the P Laplace equation, you would expect it to be r in space, r to the p in time. You cannot do it in these cylinders. You have to somehow stretch the cylinders according to a certain factor. Let me call it A0. And then you have to do the analysis, this iteration thing. So these cylinders that shrink to the point, they have to be scaled according to the nature of the PDE, according to the degeneracy of the PDE, in such a way that when you rewrite these Kachopoli estimates over these new cylinders, these new boxes, then you recover the homogeneity. Okay, this is the idea. So how do we implement this general idea? So we start with a cylinder. Okay, this is this big cylinder that we start with just to fix things. We measure the oscillation of a solution in this cylinder. Let's call it omega. So this is the difference between the supremum and the infimum. And then we do this rescaling. So we stretch the cylinders in time according to a constant that is defined in this way. So it's the oscillation of the solution divided by a constant to the power 2 minus p. So in principle, this is of course a large number because you see, I'm talking about the case p greater than 2. So the oscillation is typically a small number. You divide it by something which is large, so this is even smaller, and then you take it to a power which is negative. So this is in principle, of course, a large number. So you are in fact stretching the cylinder. And let me make two comments. First, if p is 2, I mean, A0 is 1, and you get exactly the standard parabolic cylinders. So r squared r. The other comment is that look how this constant here, A0, so this is the oscillation of a solution divided by a constant to the 2 minus p. See how it compares to this thing that we want to get rid of, which is the solution divided by a constant to the 2 minus p. So these things are very similar, right? And this is exactly the way we're gonna absorb this degeneracy. How? Okay, we have a term like this, we have power 2 and power p, right? We want to make this p throughout. So typically, we are choosing these numbers. They are related to the supremum and the oscillation and so on. So typically, k is going to be chosen as, for example, the supremum of a solution minus the oscillation divided by a constant. Okay, if we do that, so you'll see that u minus k plus is going to be, I mean, it's either 0. When it's not 0, it's just u minus k. And u minus k is u minus this guy plus omega divided by c. And of course, since u is less or equal than its supremum, this is less or equal than 0. And all this is less or equal than omega divided by c. So when I have the square, I can write it as power p multiplied by power 2 minus p, right? Of course, these two exponents add to 2. So this is exactly the same thing. This guy I keep here. And this one, you see, since u minus k plus is less or equal than omega divided by c, and this guy is negative, so this is going to be greater or equal than omega divided by c to the same power. And this is precisely my A0, okay? Omega divided by c to the power 2 minus p. So I can replace the square by the power p if I multiply by this constant a0. So, and this is what we do. So I replace the 2 by a p, and I pay the price of having a0. Then what I do is that I divide by a0 throughout. So I take it out, and it appears here as 1 over a0. And finally, I make a change in the time variable and rewrite the estimates over the new boxes, right? And so let's say that the geometry of the boxes absorbs this thing, right? Because this is the Jacobian of the transformation. And the estimates become homogeneous written over the new boxes, okay? So the mantra for this is that the equation behaves in its own geometry like the heat equation. So we recover homogeneous estimates if we write them over boxes that are scaled intrinsically, because the scaling factor depends on the solution itself. That's why we call it intrinsic. And if we rewrite the Kachopoli estimates over these rescaled boxes, we get homogeneity, which is what we need for the proof to carry on. So this was the brilliant idea of Di Benedetto. So from, I would say, the mid-1980s. And from then on, we got a much better understanding of the behavior, the local behavior solutions of singular and degenerate PDEs. So I described what is done for the degenerate case, so p greater than 2, but of course, there's a parallel theory for the singular case when p is less than 2. And so we know since the 1980s that solutions...
Sorry, José Miguel, sorry, there's a question by José Francisco. Is the method of intrinsic scaling applicable beyond? I don't know if there's something missing in there.
Well, I understand the question as if we can apply it to other equations and not only the P Laplace equation that I'm talking about. Maybe this is the, let me see. Not yet finished the question. Okay, so if that is the question, the answer is yes. I mean, you can apply it to several equations that are singular or degenerate. And this is what people did after the pioneering work of Emanuele. For example, okay, no, it's to Orlik-Sobolev spaces. Well, I'm not sure if I understand the question. I mean, because I mean, we don't apply intrinsic scaling to Sobolev space. You mean to equations involving? Well, let me just say generally, the method is very flexible, right? It applies to many equations, but I mean, I don't know exactly what you mean by Orlik-Sobolev spaces but I mean, we can discuss it later. Okay. Good, so we have this qualitative type of information. So we know that solutions of equations of this type, and they can be the P Laplace equation, it can be the porous medium equation, it can be, I mean, the equations involving singularities coming from phase transitions, for example. We'll see that in a little while. We know that solutions are, say, Hölder continuous, for example. But the information the method gives us is purely, as I said, qualitative. We know solutions belong to this regularity class. I mean, we have no information whatsoever, for example, about the Hölder exponent. We know there is a Hölder exponent, a very small number, but we have no information about the precise value of this exponent. And this is something that we started to worry about more recently, trying to give quantitative information about this. And we can call this class of methods geometric tangential analysis, because these are based on, again, on iterative arguments, scaled, of course, because I mean, you have again to do this scaling, adapting to each PDE. And the main idea is that when you treat homogeneous equations, I mean, the space of solution is somehow tangent to a space of solutions of the homogeneous problem, which have better regularity properties. And you want to import this regularity, this better regularity, and you have to correct it through the scaling to get sharp regularity results. And we've done this with a series of co-authors. So the first result I want to tell you about concerns exactly the parabolic Pillar plus equation in the degenerate case p greater than 2. This is a joint work with Eduardo Teixeira, who is in Orlando, Florida, in the United States. And what we showed is that when you have a non-homogeneous equation with a right-hand side, which is LQ in space and LR in time, solutions that we know are Holder continuous have exponent, which is precisely this number alpha that's written over here. So we derived an explicit form for the Holder exponent, depending only on the space dimension n, of course the p, and the integrability of the right-hand side, q and r. And so, of course, we have to make some assumptions on the integrability. So you want f to be sufficiently integrable. So r and q have to be sufficiently large so that this condition is satisfied. So this is what gives you access to the Kachopoli estimates and the Holder regularity. This is the minimal assumption that you need to make to get the Holder continuity, but you don't want them to be too large, in which case you enter the C1 alpha regime. So if you want to look for the best Holder exponent, I mean, if solutions are C1 alpha, they will of course be local Ellipticity, and the problem is not interesting. So we remain in this range. So Q and R cannot be above a certain threshold given by this condition. I mean, in the elliptic case, these two conditions amount to this, which is probably very familiar to people working in elliptic degenerates, working with the elliptic degenerate equations. Okay, and I mean, if you have these two restrictions in mind, then you understand a little bit better the exponent alpha, because you can rewrite it in this form. So believe me, this is precisely equal to this if you do the computations. And with these assumptions, so you have that this guy here is positive, and so is this one. And then you see, of course, that this alpha is positive because, I mean, everything is positive here, and is, of course, less than 1 because, of course, the denominator is larger than the numerator in this fraction. So you get a legitimate Holder exponent between 0 and 1. And then you can see how sharp this is. So if you project this into the linear case, p equals 2, you get exactly the optimal Holder exponent for the non-homogeneous heat equation. This was known by different methods. And if f does not depend on time, so if r is infinity, you get exactly the optimal exponent that was already obtained for the elliptic case, which is this alpha here. Another thing you can do is to try to dim the p and see what happens when p goes to infinity. So this exponent alpha is an increasing function of p, because I mean, if you differentiate with respect to p, you see that the derivative is positive. So the larger the p, the larger the alpha, and in fact, as p goes to infinity, the alpha converges to 1, which is somehow consistent with the regularity of solutions of the infinity Laplacian problem, which are, of course, Lipschitz. Okay, so we also treated the case of degenerate phase transitions. So let me say a few words about this. There's going to be a talk this afternoon at 3, where this question is going to be addressed, the derivation of the modulus of continuity for solutions of the Stefan problem, the two-phase Stefan problem, basically. So here we are dealing with a PDE of the following form. So the principal part is exactly the P Laplacian as before, but here we don't have the derivative, the time derivative of u. We have the time derivative of u plus something. Let me explain you what this is. So to simplify and to explain in very quick words the Stefan problem, when you hit an ice cube, so what you see is that as the energy increases, the temperature goes up until it reaches, say, 0, and then you continue to hit the ice cube, and the temperature remains at 0 for a certain time, and then it goes up again, right? So this amount of energy you have to give to the system for the phase transition to occur is what we call the latent heat of the phase transition. So if you invert this thing, you get that the relation between, so here this is temperature as a function of the energy, this is energy as a function of the temperature. You see that you obtain what we call a maximal monotone graph, right? So because here we have this jump. And so when you write the problem, the Stefan problem in the weak form, what you get is that here you don't write the derivative of the temperature, but you have to write the derivative of the energy. Okay, and the energy is this. It's a choice in this graph, which is u plus this latent heat. This is the heavy side. This is the heavy side function. So basically, it's a choice in this graph. Okay, that's why here I don't have equality, but I have this inclusion, right? And so what we did, and this is work done with Paolo Baroni, who is now in Parma, and Tuomo Cusi, who was in Aalto at the time and is now in the University of Helsinki. We proved this first for interior, first in the interior and then up to the boundary. We proved that, so we knew that solutions were continuous for this problem, but we derived this precise modules of continuity that I've written down here. And the improvement was in fact threefold with respect to the known literature, because I mean, what was known in the literature were results again from the early 1980s, both by Di Benedetto and Caffarelli and Evans. So Di Benedetto did it for general structures, but with a linear growth with respect to the gradient, allowing lower order terms and so on. And Caffarelli and Evans did it for the explicit case of the Laplacian. And so they obtained this type of models of continuity. So we improved this in three ways. So first of all, we generalized to any P, right? So the principal part can grow non-linear with respect to the gradient. The second improvement was that we gave an explicit form of this exponent here. So the exponent has exactly this form. So even for P equals 2, this is new. And the main improvement is that we got rid of one iteration of the log. So we got rid of one log here. So our models of continuity for the two-phase case resembles what was known for the one-phase case. So with just one log over here. So very briefly, there are also results for the porous medium equation. Since I'm a little bit over time, for the Trudinger.
No, don't worry, you have time to finish.
Okay, so but that's basically what I wanted to say. So another famous degenerate PDE is the porous medium equation. So the degeneracy here is a little bit different because you don't get degeneracy at critical points, but at points where the function itself is 0. Okay, so the equation is essentially different because compared with the P Laplace equation, here you cannot add constants to a solution. And this is a dramatic difference with respect to the P Laplace equation. The optimal regularity class here is going to be Holder. So for the P Laplacian, we know that solutions are C1 alpha. So in this case, solutions are just C0 alpha. And the other difference is that we do not know the optimal regularity for the homogeneous case. So this is a very interesting open problem. It's also only known for dimension 1. In higher dimensions, we don't know what is the optimal regularity, and that's why, I mean, our result depends on this unknown optimal regularity, optimal Holder exponent for the homogeneous case. Okay, this is basically what I just said. And we also have results for Trudinger's equation, the one that is homogeneous that I talked about at the beginning. And again, we don't know the optimal regularity for homogeneous, for the homogeneous case. But I mean, in both cases, again, we obtain somehow explicit expressions for the Euler exponent, depending only on the data of the problem. And all these things, I mean, they somehow match what we know already. And they all, I mean, they all talk to each other. I mean, these exponents, they are in accordance. I mean, so for example, here, I mean, if you compare this with what you get for the P Laplacian, when you get P equals 2 here, I mean, you can see that what you expect is exactly what you get. Okay, so that's all I wanted to talk about. Thank you very much. And
thank you very much.
I'm happy to answer your questions if...
Yes, now there is. So maybe I could read it because I'm not sure that everyone, all the others can. So let me just read it while you... So my question is, by Jose Francisco, is the intrinsic scaling for the P Laplacian is of the power type. Is the method applicable to other nonlinearities involving convex functions that yield solutions in orderly Sobolev spaces?
Well, I don't know the answer to your question exactly. I've never seen anything like this, but as I said before, the method is very, very flexible. So, and I mean, can be applied to different nonlinearities, for example, the ones in the porous medium equation. So I would say, I mean, it's worth trying applying the method. The method is in fact very flexible, and you can apply it to, I mean, different PDEs that share this some sort of degeneracy or singularity. I did it, for example, for equations describing the mixtures of fluids where you have a degeneracy in two different points. For example, when U is 0 and when U is 1, okay? And it's also possible to adapt the method to treat these cases. So, I mean, probably yes, but of course, I mean, you would have to try to be sure.
So while we wait for the questions, let me also make a question. So in your title, you have sharp regularities. Are all the results that you presented sharp in the sense that you have counterexamples for?
Well, maybe I was a little bit, I cheated a little bit in the title. I mean, here sharp, I didn't use the word optimal because as you were saying, to show that the results are optimal, you would have to have counterexamples.
Yeah, and I
showing that you cannot go beyond this. So what I can say is that, for example, for the P Laplace equation, when you project this in the linear case, you get optimal, the optimal regularity. So I would say that at least some of these results are indeed optimal.
Mm-hmm.
But to be entirely honest, we don't have counterexamples that prove this. Mm-hmm. So in fact, I don't know if they are optimal, but at least they are sharp in the sense that they are precise, that you have this.
It was sharp. Okay.
Yeah, sharp in this sense.
But then when it reduces to the classical case, it coincides with what is known.
With the optimal, and this you know, yeah.
Nice. So I didn't say.
Well, in fact, in the elliptic case, we also did something that I did not mention today because I wanted to talk about parabolic problems. But for the case of the elliptic P Laplace equation, non-homogeneous with right-hand side, with bounded right-hand side, we proved together with Eduardo and Damião Araújo, also from Brazil, that solutions are in fact C1 alpha with alpha equals 1 over P minus 1. And this is known to be optimal because there are counterexamples. Okay, and we managed to prove this conjecture, but unfortunately only in 2 dimensions. Mm-hmm. Because it's only in 2 dimensions that you know what is the optimal regularity for the homogeneous case. And you obtain this in 2 dimensions by complex analysis methods that are not generalizable to higher dimensions and quasi-conformal mappings and things like this. So in this case, we have counterexamples and the result is indeed optimal. But for the problems I mentioned, the optimality is only when you project into the linear case. You get the optimal exponent.
Thank you. Yeah. So I don't think we have more questions. So first of all, about the
I think there's one.
There's one? Ah, yes, sorry. Right? Okay, let me just read it. So the approach to get optimal exponent makes use of harmonic inequality, right? What if one only has intrinsic or weak or very weak harmonic inequalities?
No, in fact, it does not use the harmonic inequality. So it doesn't use the harmonic inequality. So that's the short answer to your question.
Okay. So thank you very much for this talk, José, because I imagine it's a challenge to present it, and you really did a very good effort, starting with the classical estimates and then showing what is the building block and then ending to what I imagine it's a very difficult topic. And yeah, I'm very curious about this intrinsic scaling. You sold it very well, I must say. So I think it was a very good tribute, like you intended.
Okay. Thank you.
So if there are no more questions, let me finish by thanking once again to our four wonderful speakers. I think they were very good, four very good talks, and I'm very happy to have you as speakers. So thank you, and hope to see you in the near future. Well,
okay, thank you all. Bye bye.
10 minutes. That's for the others.
Yeah.